Okay, so 10.3 is on polar coordinates. And polar coordinates are just special parametric values. Okay, they're special parametric equations that we work with. Okay, where x is equal to r cosine theta, y is equal to r sine theta, and this will translate, okay, from r theta back to xy. You give me r and theta, a point in terms of a radius and an it will go from polar to rectangular. Okay. These are the conversion equations for polar to rectangular coordinates. Okay, we'll talk about what these coordinates are in a second. Okay, if I wanted to go backwards, if I was given x and y, and I wanted to get to r and theta, okay, I would say theta is equal to the inverse tangent of y over x, and r is equal to the square root of x squared plus y squared. Okay, and this takes me from an xy point and translated it into an r theta point. So we're going from rectangular coordinates to polar coordinates. Okay, let's take a point, okay, in space. Let's draw a grid. And let's just take a point in space. We'll call this point in space over here. Maybe we'll label this point A. Now, for our traditional location of point A, okay, in space, that location is on a grid system in rectangular coordinates. Okay, and that would be at 2, 2. That's an xy value. Okay. Well, if I change my coordinate system to angles and radii or concentric circles, okay, and maybe if we go out 3, okay, and we say that our coordinate system is now concentric circles, we can describe this point in space a little bit differently. We can describe its distance from the origin in terms of a rate, okay, or that distance from the origin, okay, and using the Pythagorean theorem, we could actually calculate what r is. This is just up to and over 2, and so this would be 2 radical 2. That's r. And then we could calculate the angle that this creates using tangent, okay? The inverse tangent, and the inverse tangent of 2 over 2, which is the inverse tangent of 1, is the angle whose tangent is 1, and that's a 45-degree angle. So we can label points in space different ways depending upon, okay, the differences in the coordinate system that we use. And each coordinate system has its strengths and its weaknesses. Okay. And when I'm describing curves, sometimes the curves can be very circular in nature, and actually it's easier to describe them using a polar coordinate system or a circular reference system. Okay. Okay. Let's look at number one here. Let's sketch a polar curve. Sketch a polar curve with equation r equals 2 cosine theta. R equals 2 cosine theta. Okay, so this is a polar curve. Oops, forgot the RV there. Yeah. With equation r equals 2 cosine theta. So this is a function of theta. Okay, you could replace r with f of theta if you really wanted to. Okay, this is a function of theta. Theta is the independent variable and r is the dependent variable. R depends on where I am on theta. So as I draw my curve, whatever curve this looks like, okay, the radius that I'm out depends on the angle that I'm at. And so different angle will create a different radius. And a different angle as well creates a different radius. Okay, and so it depends on R1, R2, R3. It depends on my angle. Okay, the angle will determine how far out I am from the center, from the origin. And that will determine what curve or what shape I am creating. Notice that with polar coordinates, it doesn't matter that we violate the vertical line test. Okay, because we're going around in a circle. Okay, we can have functions that have tops and bottoms. Okay, and so that's one of these things. If I were to try to draw a circle and label that as a function, I would actually have to piecemeal that into two different functions. If I had the top of the circle and then the bottom of the circle, I'd have to write that circle as two different functions because this would violate the vertical line test. But if I just wrote this as r equals 3 in polar coordinates, well, that doesn't violate the vertical line test. And so it's just one function. Okay, whereas before I would have had to write this as y equals negative square root of 9 minus x squared and y equals positive square root of 9 minus x squared to get both the top and the bottom. Okay, here I just write it as r equals 3 and we're done. Okay, so that would be a circle of radius 3 through with a center of 0, 0. Okay. So it can be handy and convenient to use polar equations. So let's try to draw r equals 2 cosine theta in polar coordinates and see what we get. Okay. Okay, so let's look at different values of theta here. Okay, so I'm going to build my function here for r. I would say theta, and then cosine theta, and then 2 cosine theta, and that's going to be equal to r, right? And so once I get r, this is r. Once I get r, I can write it in terms of a polar coordinate theta r. Okay, so I'd like to use some nice reference values. If I take theta equaling 0, okay, let's just look at our polar graph, polar grid. If theta is 0, okay, that means I'm at 0 degrees with the x-axis. Okay, or with the 0 axis, basically. Okay, this is 0 degrees. Oops, looks like an 8. 0 degrees is here. That's the 0 axis. Okay, 90 degrees is here. This is the pi over 2 axis, or 90 degrees. Okay, so at 0 degrees, or sorry, we'll keep it in radians. 0 radians and pi over 2 radians. Okay, at 0 radians, the cosine of 0 is 1. And 2 times the cosine of 1 is just 2. Or cosine of 0, which is 1. 2 times 1 is 2. And so this becomes 0 is the degree angle, or the radian angle, the radian measure, and r is equal to 2. Okay. It doesn't matter if you use degrees or angle or radians, it'll come out the same. Okay. But what we want is we want to be out at 2. Okay. 0, 2. Okay. Now that's not 0, 2 as in 0x, y 2. That's 0 degrees, and my radius, which I'll put in green, which is r, is out 2. I'm starting at 0 degrees, or sorry, 0 radians, and I go out 2 units. Okay. The next thing that I want to look at is what happens at pi over 4. Okay. So at pi over 4, the cosine of pi over 4 is radical 2 over 2. And 2 times that is radical 2. And that's going to give me at pi over 4, I'm at radical 2. Okay, so pi over 4 is 45 degrees. Okay, and so then I'm at radical 2, which is actually right here. Okay, it's a 1 by 1 by radical 2. Okay, right triangle. Okay, so that point is right there. Okay, and then let's go to pi over 2. Well, what happens at pi over 2? The cosine of pi over 2 is 0. So this becomes 0. And so at pi over 2, we're at 0. Remember, cosine is my x value on the unit circle. So we are here at 0. Okay. And so now, where are we going to go? We're going to go to 3 pi over 4. So at 3 pi over 4, and this is going to be very interesting, at 3 pi over 4, okay, we're over here. Okay, but at 3 pi over 4, the cosine of 3 pi over 4 is negative radical 2 over 2. It's in the second quadrant. And so this becomes multiplied by 2, that becomes negative radical 2. And so this becomes 3 pi over 4 and negative radical 2. Well, what does it mean to have r be negative? Well, if your r is negative, a negative r means that you're going in the opposite direction. So whereas you would think, oh, well, my r would go out this direction because it's 3 pi over 4. Yeah, it would only go out that direction if it were positive. But it happens to be going negative. So I have to go negative radical 2. Okay. And so it goes out here. Okay, and then at pi, where are we? At pi, we are at cosine theta is negative 1. And so this is negative 1 times 2 is negative 2. And so this becomes pi and negative 2. Okay, so what does that mean? That means that if I go out pi units, it's half a circle, I have to go negative 2 in the negative direction. So that's, instead of going positive, I'm going to go negative 2. Well, that ends up right here. I'm back where I started. After a period of pi units, I'm back where I started. And what does this create? This actually creates a circle. If I were to plot every single value here, okay, this actually creates a circle, okay, centered at 0, 1 with radius 1, or sorry, 1, 0 at radius 1. So that's what this is creating. This r equals 2 cosine theta creates a circle, okay, of radius 1, circle of radius 1 at center, at a center of 1, 0 in the xy coordinate system, okay? In the theta r coordinate system, it would be 0, 1. Okay, but in this is, I'll label this as xy. Okay, because I really want to compare this to the xy. How would I compare r equals 2 cosine theta? What if I wanted to change that equation back to a rectangular coordinate equation? Well, I do have something that will relate cosine, right? Because I said that x is equal to r cosine theta, right? And so if I were to solve for cosine theta and divide by r, I know that cosine theta is equal to x over r. And I could actually just plug that back in. Okay, so this would become r equals 2x over r. Okay, so that gave me an x, but where's my y? Well, if we multiply both sides by r, I'll get the r's to cancel out, and I'll get an r squared. So this is r squared equals 2x. Okay, but what is r squared? Well, r was equal to the square root of x squared plus y squared. If I square both sides, I get r squared equals x squared plus y squared. And so this becomes x squared plus y squared equals r squared, which is what's right above it, is equal to 2x. Now, if I really wanted to be cheeky, I could move this over. When I get x squared plus y squared minus 2x is equal to 0. Let's rearrange this to x squared minus 2x plus y squared equals 0. And now let's complete the square, having the x together. Half of negative 2 is negative 1. So negative 2 divided by 2 is negative 1. Square that bad boy, and I get 1. And that's what I want to add to both sides to keep it balanced. So x minus 2, x squared minus 2x plus 1 plus y squared equals 0 plus 1. Now I want to factor this guy into x minus 1 squared plus y squared equals 1. Now, I could square the 1 as well if I wanted to, take the square root and then square it. And what does this tell me? This tells me that if I take r equals 2 cosine theta, then this is the same thing as in polar coordinates as in the equation of a circle, right, in rectangular coordinates. And where is that circle located? That circle is located at 1, 0, center 1, 0. And what's the radius? Radius of 1. So we do end up getting the exact same value, okay, the exact same graph. Whether we use polar coordinates or whether we use rectangular coordinates, the shape that's drawn is exactly the same. Okay, we can see this with computer generated graphs as well. If we go to Desmos graphing calculator, okay, we can actually work in rectangular or polar coordinate systems. Okay, if I want to change my grid here from a rectangular grid, okay, let's just look at what we did earlier. We had point we have 0.22. Okay, maybe I'll label that. Okay, 0.22. Comma 2. Okay, label. Okay, so we'll label that 0.2 comma 2. That's in the XY coordinate system. If I change my grid, I could change my grid here from a rectangular grid to a polar grid. Okay, and so let's see if this will work. If I do radical 2 comma pi over 4, will that work? Let's see. So let's see if the computer understands what I'm trying to do here. Radical 2, no, it's 2 radical 2, sorry. 2 radical 2 and pi over 4. Okay, pi over 4. I don't think so. I think it's going to keep it in rectangular, but we'll pi over 4. Yeah, it doesn't like that. Oops. Okay, yeah, it's not working as desired. Okay, it's fine. Because it's just changing the pi over 4 into 0.57 something, which is fine. Okay. However, I do believe that if we do this, x squared, oops, is 2x plus y squared equals 0. We get that guy there. And if we do r equals 2 cosine theta, equals 2 cosine theta, theta, okay, you can see that they are identical. Okay. So the purple one is on top of the green one. Okay, those are identical circles. Okay, I can't go point to point though, which is sad. Okay, but yeah, which is cool. And this is going 0 to pi for theta, which is just one cycle anyway. We could go 0 to 2 pi, but then it would just cycle twice over the same place. We did 2 pi. It would just cycle twice. Okay. 0. If we did pi over 2, it should just give me half the circle. So, feel free to play around with this yourself in dealing with these. Yeah, you can see that just gives me half the circle. Okay, because the circle has a period of pi. Okay, and we can see that those are identical circles. Okay. Okay, we'll come back to this. Okay, so if we wanted to do point to point, right, how would I translate, going back to that 2, 2, how could I translate this from rectangular to polar, right? How could I translate that from rectangular to polar? Well, again, this is X and Y, right? And so we would use the fact that theta is equal to the inverse tangent of Y over X. So that's the inverse tangent of 2 over 2, which is the inverse tangent of 1, which is 45 degrees. So that's a 45-degree angle, or pi over 4. Okay, R is equal to the square root of x squared plus y squared. Okay, and so this is equal to R equals the square root of 2 squared plus 2 squared, which is equal to the square root of 4 plus 4, which is the square root of 8, which is 2 radical 2. Okay, so we've got our theta, pi over 4, we've got our R of 2 radical 2. So 2 radical 2 and pi over 4 is in polar coordinates is the same as my rectangular coordinate above. And we could go backwards as well if we wanted to. If we want to go from polar to rectangular, we could go backwards as well. We could just plug it into the other formulas. R is equal to cosine, sorry, X is equal to R cosine theta, and Y is equal to R sine theta. Okay, so we could say, oh, well, this is going to be 2 radical 2 times the cosine of pi over 4, and this is equal to 2 radical 2 times the sine of pi over 4. But what is the cosine of pi over 4? It's 2 radical 2 times radical 2 over 2. And this is 2 radical 2 times radical 2 over 2 for sine pi over 4. Going back to the unit circle, and that 2's cancel out, and radical 2 becomes radical 4, which is 2 and 2. So that checks. Okay, we can go forwards and backwards. Okay, let's try the sketch of another one. Okay, one that's a little bit more complicated. Okay, number 2 here, sketch. Let's spell sketch. Sketch R equals 1 plus sine of theta. Okay, R equals 1 plus sine theta. So again, we get some values here. Theta, sine theta, 1 plus sine theta, and this one has a period of 2 pi, so if it go all the way around to 2 pi, I want a lot of reference points, so I really know what the shape of this thing is doing. Okay, that's gonna, and then I'm gonna have r theta as my point, okay, because this 1 plus sine theta is r. Okay, so when theta is 0, the sine of theta is 0, and 1 plus 0 is 1, and so this is at 1, 0, 1. Okay, oops, 1, 0. Okay, at pi over 4, the sine of pi over 4 is radical 2 over 2. 1 plus radical 2 over 2 is going to be 1 plus radical 2 over 2. Okay, and we could get an approximate value for that if we wanted to. That's approximately 1.707 comma pi over 4. Okay. At pi over 2, we're going to be at 1, and then this is 2, and so this is 2 pi over 2. At 3 pi over 4, this is, the sine is still radical 2 over 2, so it's just 1 plus radical 2 over 2, which is equal to 1.707 approximately. and 3 pi over 4. Okay. At pi, sine of pi is 0 again. And so this becomes 1, and this just becomes 1 pi. Okay. Now what about 5 pi over 4? 5 pi over 4, the sine of 5 pi over 4 is negative radical 2 over 2, so negative radical 2 over 2. So this is 1 minus radical 2 over 2, which gives us approximately 0.293. Okay, and then that's at 5 pi over 4. And then at 3 pi over 2, we're at negative 1. This becomes negative 1 plus 1, which is 0. So this becomes 0 and 3 pi over 2. Maybe a couple more. 7 pi over 4 is going to be the 4 is negative radical 2 over 2 again. So this is 1 minus radical 2 over 2, which is approximately 0.293, and and 7 pi over 4. And the last one is 2 pi. We've gone all the way around the circle, and we get 2 pi. The sine of 2 pi is again 0. So this is 1. And so we're basically back where we started. It's 1 and then 2 pi, which is essentially 0. So we've made full circle. Okay, so let's plot these points, shall we? Okay, let's figure out what's happening with our graph. Stop. Just draw a straight line, please. Thank you. Okay, so I'll draw it in blue. Okay, just so that it doesn't get messy with the coordinate system that I drew. Okay, 1, 0. Where's 1, 0? R is 1. The radius is 1, but the angle is 0. That's going to be here. Okay, 1, 0. Maybe we'll make 1 go out 2 spaces. I don't know. Make 1 a big one. Okay. Here's 1 and here's 1. Okay, and so we get that guy there. Okay. And then this is going to be 2 up here. Okay, and then at pi over 4, again, where's pi over 4? It's the pi over 4, we're just the line y equals x. And my 3 pi over 4s are at the line y equals negative x. So we got those values there. Don't like that. Okay, so at pi over 4, we're at 1.707, or 1 plus radical 2 over 2. So radical 2 is 1.41, right? So radical 2 would be right here. That would be radical 2, which is approximately 1.41. We're a little bit farther out than that. Okay. Again, radical 2 is approximately 1.41, right? If you're doing on your calculator. I'm a little bit further than that. I'm 1.7. So I'm a little bit further out than radical 2. And again, how did I get radical 2? I just triangulated this 1 by 1 box. The diagonal of a 1 by 1 box is radical 2. So this point, red point, is radical 2. The blue point, okay, is a little bit further. I'm kind of eyeballing it, and that's going to be at 1.707, okay, roughly. Okay, the next one, we're at pi over 2, okay, which is 90 degrees. Okay, so we've gone 90 degrees now. Pi over 2, we're out 2, so that's right here. Okay, so we're getting a curve that kind of looks like this. Okay, nice. Okay, and then at 3 pi over 4, we are out. Okay, we're out a little further than pi over 2. And I'm sorry, a little further than my radical 2. So that's radical 2, which is not our point. Our point is out here, a little bit further. So we're gonna go around. Down. Okay, and then where are we gonna hit next? Next, we're gonna be at pi, and we're gonna be at 1. So we're gonna hit 1 down here at pi. We're gonna be at 1. Okay, so okay. And then what happens? Well, then at 5 pi over 4, which is down here, we're only at 0.293. We're very shallow here. Okay, and so we're there. And at 7 pi over 4, we're at the same spot. We're there. And then at 3 pi over 2, I kind of jumped 3 pi over 2. But at 3 pi over 2, we're at 0. We're kind of going like this. And then coming in, and then we would go back to where we came from, and we get this shape here. Okay, this shape is called a cardioid. Cardioid. What how you say cardioid? Cardioid. Cardioid. Maybe I'm missing an I. Cardioid. Cardioid. Yeah, cardioid. Okay. Although I was missing an I. Okay, it's called a cardioid. Cardiac means heart. And so this is a heart shape. Okay. And it's kind of upside down heart, the way that we've drawn it here. But this is a cardioid. Okay, and it has this kind of special shape there. There are a lot of special shapes, okay, in polar coordinates. Okay, we can have spirals, we can have circles, we can have lines, we can have parabolas, okay, we can have cardioids, okay, we can have what's called a lemon skate, which looks like this. It's when the cardioid loops around on itself. Okay, so lemon skate. So different shapes created through this. Okay, now some of you may have had this in pre-calc. Some of you may not have. That's why I spent a lot of time, almost an hour, on this topic, just to make sure that everybody's up to speed. Okay, but now I would like to do some calculus. Okay, let's do some calculus on this stuff. Okay, so for example, okay, what would be the derivative of the cardioid at pi over 3? We didn't even do pi over 3, but pi over 3 would be right here, right? Okay, what would be the derivative, or what we would call the slope of the tangent line? Okay, what would be the slope of the tangent line at pi over 3, right? Because that's really what the derivative is. It's the change, the rate of change, right? And in this case, it's a rate of change could be dr d theta, but we really want the tangent line to be in terms of x and y, so we want dy dx. So we have a formula, dy dx is equal to, this is kind of similar to how we dealt with parametric derivatives, in that we say, well, we're just going to take the derivatives separately, dy d theta over x theta. Okay. Okay. However, what was x? Well, x was r cosine theta, right? So what is dx? D theta. What's dx in terms of theta? Well, wouldn't it be r and then the derivative of cosine theta, which is negative sine theta? Right? Except for the fact, and here's the thing, is that r is not a constant. R is not a constant. See, R in any polar equation is a function of theta. So the way I really should be writing R is R theta cosine theta. It's really a function of theta. Okay, and so what we can't just let R be a constant because it's not a constant. It's not constant. If you look at my cardioid, my radius here is not constant. It changes. Okay, my R changes depending upon where my theta is. Okay, so R is not constant. So R is a function of theta, and cosine is a function of theta. So X is a function of theta. And so dx d theta is going to be using the product rule, derivative of the first, which is r prime of theta, times the second, cosine theta, okay, plus r theta times the derivative of cosine, which is negative sine theta. And I can rewrite this a little nicer and saying that r prime of theta, I can rewrite that as dr d theta cosine theta minus r theta, which is r, sine theta. Okay, so that's what's going to go on the bottom here. On the bottom of our formula to translate dy dx into dr d thetas, it's going to be dr d theta cosine theta minus r sine theta. Okay, and likewise, we're going to do the same thing with y. Y is equal to r of theta sine theta. Okay, and so dy d theta is going to be equal to r prime of theta, okay, times the sine of theta plus r of theta times the cosine of theta. We have a plus because the derivative of sine is cosine. And so again, we can write this as dr d theta. Okay. Dr d theta, which, you know, maybe getting some flashbacks of trig substitution. Okay, we're substituting variables here. The r d theta of sine theta plus r cosine theta. So that's what goes on top here. The r d theta sine theta plus r cosine theta. And so we can use this handy dandy formulae, okay, to help us translate derivatives in terms of polar functions. Okay. So let's look for dy dx. X is equal to dr d theta of sine theta plus r cosine theta all over, oops, all over dr d theta cosine theta minus r sine theta. And what's the polar function that I'm working with? I'm working with, I want, let's put this example 3, for the cardioid, okay, for the cardioid, r equals 1 plus sine theta, which is what I have above, find the derivative do I really want to find the derivative? Yeah, we'll just find the derivative. That's fine. Find the derivative, aka slope of the tangent line to the cardioid at pi over 3. Theta is equal to pi over 3. And find the derivative, aka slope of the tangent line, to the cardioid at theta is equal to pi over 3. So let's plug this in. Well, what do we know? We know what theta is. We do not know what dr d theta is, but we do know what r is. R is equal to 1 plus sine theta, right? Okay, but what is dr d theta? Dr d theta is the derivative of this. Well, that's just cosine theta. Okay. So now we're just going to say, well, dy dx is equal to dr d theta, which is cosine theta, times sine theta plus r. But what was r? R was 1 plus sine theta, right? So this is 1 plus sine theta times cosine theta. Okay. Nice. Okay. So that's the top. What's the bottom going to be here? The bottom is going to be dr d theta, which again is cosine theta, right? Times cosine theta plus, or minus this time, minus, a minus 1 plus sine theta times sine theta. Okay, interesting. Okay, so this is equal to dy dx is equal to, let's factor out a cosine on top. Cosine theta times, this is going to be 1 plus 2 sine theta. Okay, interesting. Okay, on the bottom, we get cosine squared theta minus 1 minus sine squared theta. 1 minus sine squared theta. Interesting. Okay, so dy dx. At any point, we can plug into n pi over 3. Maybe I'll simplify just a tiny bit more. This cosine squared minus sine squared, that's, I believe, a double angle formula. Is that right? Cosine squared minus sine squared is a double angle formula, right? Of cosine 2x. Yes. So that's cosine of 2 theta. This is cosine theta times 1 plus 2 sine theta plus 2 sine theta all over cosine 2 theta minus 1. Okay. That's good. Cosine 2 theta minus 1. That is an identity itself as well, but let's not get too carried away. Okay, I just wanted to try to simplify this as much as possible. Hmm. Cosine 2 theta minus 1. That's negative 2 sine squared theta. But again, I don't need to get too fancy. Okay, with everything. So let's plug this in. Let's say that this is cosine of pi over 3 times 1 plus 2 sine of pi over 3 all over cosine 2 times pi over 3 minus 1. Okay. Okay, so cosine of pi over 3. Cosine of pi over 3, that's the x of pi over 3. I believe that's 1/2. Okay, so that's 1/2 times 1 plus 2. The sine of pi over 3 is radical 3 over 2. Okay. Nice, 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 nice. Okay. That just becomes 1/2 times 1 plus radical 3. Yes. Okay. All over cosine of 2 pi over 3. Well, cosine of 2 pi over 3 is what? Cosine of 2 pi over 3 is, let me think about that for a second. Isn't it just negative 1/2?
Yeah, negative 1/2.
Okay, so negative 1/2. Okay. Okay, and then, oh, you know what? I messed up. I'm sorry. I messed up here because this is not 1. This is not 1. I forgot to distribute the sign to both of these. This is sine. Okay, it won't mess up anything too badly, but that's okay. Okay, so that's not a 1. That's minus sine of pi over 3. Okay, and sine of pi over 3, okay, that's minus radical 3 over 2, right? So if I factor out a 1/2 from the bottom, I get 1/2 on top, and that's 1 plus radical 3. If I factor out a 1/2 on the bottom, or let's factor out a negative 1/2 on the bottom, I get 1 plus radical 3. And so those cancel. And so I'm left with 1/2 over negative 1/2, which is just negative 1. So the slope of the tangent line at pi over 3 is negative 1. That's kind of crazy. Okay, so this slope way back here is negative 1. Okay. Interesting. Interesting, interesting, interesting. Okay, but what if I wanted the equation of the tangent line? Where is this? Right? The tangent point is at theta equaling pi over 3, right? So what would r be there? R would be the sine of pi over 3 plus 1, right? So r is equal to the sine of pi over 3 plus 1, or 1 plus the sine of pi over 3. So I have a point. Let's go back down here. Okay. If I wanted the tangent line, the equation of the tangent line. Okay. We know that theta is equal to pi over 3. So we already have our theta. But what's r going to be equal to? Well, r is equal to 1 plus sine theta. Right? So r is equal to 1 plus the sine pi over 3. And the sine of pi over 3 is radical 3 over 2. This is 1 plus radical 3 over 2 is equal to r, right? Okay, so we have this in terms of r theta, 1 plus radical 3 over 2 and pi over 3, and that's in terms of r theta. But if I wanted to write the equation of a tangent line, I would want it in xy coordinates, right? I would want that in xy coordinates. Okay, so how am I going to write this in xy coordinates? Well, let's just change r theta into xy. So x is equal to r cosine theta, and y is equal to r sine theta. Okay. So what is r? I'm gonna rewrite r as 2 plus radical 3 over 2. Okay, and then times the cosine of pi over 3, that's just 1/2. Right? So that's x equals, okay, 2 plus radical 3 over 4, right? Okay, good. Okay, so that's my x coordinate. Okay, what about y? The y coordinate. That's just the sine of theta. Okay, so r is 2 plus radical 3 over 2, and the sine of pi over 3 is radical 3 over 2, right? So what's this going to become? This is going to become 2 radical 3, when I distribute the radical 3, plus 3 all over 4. Interesting. Okay. Yeah. Okay, I mean, I could rewrite that as 3. I could have just distributed first and to the 3 and wrote that term first. So that's going to be the square root of 9, which is 3 plus 2 radical 3, just so that they're kind of in the same form. Okay, and so what's my x? My y point is 2 plus radical 3 over 4, comma, 3 plus 2 radical 3 over 4. It's kind of a weird point, but that's where it's located. It's located, okay, on my cardioid. That's where that point is located. So that's interesting. So, so if I want to write the equation of the tangent line, I could use point slope form. And I could say, look, we have y minus y1 equals x, or sorry, m times x minus 1. That's going to be equal to y minus 3 plus 2 radical 3 over 4 is equal to -1 times x minus 2 plus radical 3 over 4. I distribute the negative. Okay, this becomes y minus 3 plus 2 radical 3 over 4 equals -x plus 2 plus radical 3 over 4. If I add, right, 3 plus 2 radical 3 over 4 plus 3 plus 2 radical 3 over 4, I can add the numerators together, and I get y equals -x plus, this is going to be 5 plus 3 radical 3 over 4. That's my y-intercept. 5 plus 3 radical, that's crazy y-intercept, but that should work. Let's check our work. Maybe I messed up somewhere. I could have messed up. Okay. What I'm doing is kind of, I'm kind of just flying by the seat of my pants on this one. Okay. So yeah, let's check this with Desmos. Okay, where is Desmos? Let's go back to Desmos, yeah. So what was the equation? The equation here was r equals 1 plus, get rid of that guy, 1 plus the sine of theta. Okay, and I don't want the 0 to pi over 2, I want the whole enchilada here. I want 0 to 2 pi. Okay, 2 pi. Okay, so there's my cardioid. Okay, now theirs is a little bit better than mine because theirs is computer generated and mine was not. Okay, but we have some nice values here. 0, 1, Okay, it's a nice, nice value there. At 0, we've got 1. Okay, we calculated these. At pi over 4, it was 1.707s. 2, at pi over 3, we calculated that one as well. Okay, you know, where that point was located. The slope of the tangent line along there is -1, and we can show that by putting in a rectangular, rectangular uh, uh, what do I want to say here? A rectangular function, okay, rectangular graph of the tangent line here. So y equals negative x, and I'm going to put a plus c here. Just y equals mx plus b. Maybe we'll put a plus b for b. Okay. So I'm going to add a slider. Yeah, I'm going to add a slider here, and it's going to say, well, what do you want the slider to do? I want the slider to go out. I want it to be my y-intercept. Okay, I want it that b needs to be my y-intercept. So no matter what I do with this slider, okay, if b is 0, it goes through the origin and it slides out. Okay, and then we're gonna let our b be our y-intercept that we calculated in our previous equation, which was kind of a weird y-intercept. It was 5 plus 3, right? Radical 3. Okay. And then we want all of that in parentheses, close parentheses, and divide by 4. Look at that. It is tangential, my friends. At where? Where is it tangential? And it should show me that there is a tangent. Okay. It's giving me in rectangular coordinates, but that's okay. At pi over 3. Okay. Right there, it is tangential. And what's the slope? The slope is -1, because that's what the derivative was. Okay, let's talk about arc length. Okay, we'll continue a little arc length here. Okay, let's do, let's do arc length. Well, if you want to do arc length, or do you want to do, yeah, let's do arc length. Okay. Okay, let's go back to, let's go back to, and let's deal with arc length first. So we're gonna go 10.4 here. Okay, arc length and sector area. Okay, so arc length and sector area. Okay, arc length and polar coordinates. Okay. So remember that arc length in rectangular coordinates was going from A to B of, okay, 1 plus y dx squared, and then we square rooted that bad boy, dx, and that's rectangular. Okay, that's in rectangular coordinates. In polar coordinates, it's a little different. We end up with an extra r squared. Okay. Okay, and so, L is equal to the angle alpha to beta of the square root of r squared now plus dr d theta squared. Okay, and this is d theta. Okay, so in polar coordinates, we're squared, and that has to do with the fact that r is a function of theta. Okay, and it just comes out to be that we're taking little pieces of the arc length, but we note the extra r squared here. Note, this is in polar. Note the extra r squared. Okay, so what if we stick with our friend the cardioid here? Um, want to find the arc length of one cycle of the cardioid. So find the arc length of one cycle of the cardioid r equals 1 plus sine theta. Okay. So what do we need to find? We need to find out, well, what's dr d theta? And dr d theta is equal to, okay, dr d theta is going to be equal to just cosine theta because the 1 goes to 0 and the sine becomes cosine theta. Okay, so let's integrate this. One cycle, theta is going to go from 0 to pi over 2. Or sorry, 2 pi. 0 to 2 pi, not pi. It's going to go from 0 to 2 pi. Okay, because that gives me one cycle. Okay, of that guy. And we're going to go L equals the integral from alpha to beta, which is 0 to 2 pi, of the square root of r squared. What was r? What was r? R is equal to 1 plus sine theta. So we have to get everything in terms of theta. That's the goal here. And then we can integrate, because we can't integrate on two variables. We can only integrate on one. Okay, so this is going to be 1 plus sine theta squared plus the r d theta is just cosine, so that's just cosine squared theta. D theta. Okay, so now we're gonna multiply this out. Okay, FOIL that out, and we get 1 plus 2 sine theta plus sine squared theta plus cosine squared theta d theta. Okay. Okay, so the sine squared theta and the cosine squared theta, they've become one because of our Pythagorean identity. And so this becomes L equals 0 to 2 pi of the square root of, this is just 1, so this is 2 plus 2 sine theta. Okay. Cool, 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 cool. Okay, d theta. Okay, so now is the sneaky part. The sneaky part is I'd really like to deal with a sine squared if I can. And not a sine. Okay, so if I can deal with a sine squared, I might be able to reduce some of this stuff. And so what I can do is I can multiply both top and bottom by the square root of 2 minus 2 sine theta over the square root of 2 minus 2 sine theta. So the conjugate. Multiply both top and bottom by the conjugate, and we'll get something that we can work with a little nicer. Okay, and so we get L is equal to 0 to 2 pi of, this is going to be the square root of 4 minus 4 sine squared theta, okay, all over the square root of 2 minus 2 sine theta, d theta. Okay, nice. It's good. Okay, what I'm trying to go for here is to set up a u/du substitution. Okay, and so I could factor out that 4, square root of 4, and then I get square root of 1 minus sine squared theta. But what is this? What is the square root of 1 minus sine squared theta? Isn't that just cosine? Because isn't 1 minus sine squared cosine?
Cosine square.
Yeah, exactly. It's cosine squared. And so the square root of cosine squared is just cosine. So this is square root. Oh, give me back my pen. Square root of 2 minus 2 sine theta. Right, so this is going to be 2. Okay, 2 times, okay, the square root of cosine squared theta. Now, this is where things get a little interesting. Okay. Okay. Because you might just think, well, that's just cosine, and it's actually not cosine. Okay. This is not cosine. Okay, it's a special form of cosine. Okay, what the top becomes here these are all d thetas, equals 0 to 2 pi, 0 to 2 pi. Okay, what the top becomes is what? See, theta is a variable. Okay, and it can vary, right? It can vary from what? From 0 to 2 pi. The problem comes with the fact that we're not going to get all the values of cosine. If I take the square root of x squared, that's what? That's not just x. What did I just do? I just eliminated all the negative values that this possibly could be. This is absolute value of x. And it's the same thing that I just did here. If I take the square root now, this is absolute value of cosine of x, of theta. Okay, so this is the absolute value. So it's a very subtle, okay, difference, but it is a difference in that this is gonna, the cosine of theta now becomes, it has to, all gonna be positive values. This forces cosine to be positive. Okay, and that's going to be important in a minute. Okay, that forces cosine to be positive. Okay, so this is d theta, and this is the square root of 2 minus 2 sine theta. Okay, nice. Okay, why is that important? Because If I want to undo the absolute value, which I do want to undo the absolute value, what happens to this? Well, if I look at a circle here, the unit circle, and I force cosine to be positive, then that's just this part of the circle. That tells me that I can only go from negative pi over 2 to pi over 2. But then how would I get the whole circle? I would have to double the area, the integral that I got. So that's exactly what I'm going to do. I'm going to double, but I'm only going to go from negative pi over 2 to pi over 2. Because if I don't do this, when I take the integral, I'm going to get 0. Okay, if I don't do this and I just remove the absolute value bars here, I will end up with an integral of 0, and that doesn't make any sense. Okay, because the integral is going to give me arc length, and I know that I can travel around the cardioid. But what's happening is that the right side of the cardioid and the left side of the cardioid are going to cancel each other out. Remember what the cardioid looked like? It looked like this. And it was extremely symmetric. Okay, and the left side, which is positive, it's positive arc length. Sorry, that's not the left side. That's the right side. Okay, the left side, which is over here, and the right side, if I just went all the way around here, I would end up with a positive arc length, and then I would end up with a negative arc, then they would cancel each other out. And I don't want that. So I'm just going to do the positive arc length, which is going to go from negative pi over 2 to pi over 2, and then I'm going to double it because it's symmetric. There's symmetry there. Okay, the left side and the right side are identical in the cardioid. Okay, so this is the square root of that guy. And so we get 2 times cosine theta. Now I can remove the absolute value bars over the square root of 2 minus 2 sine theta d theta. Now I can do a u du substitution, which is nice. I can say u is equal to 2 minus 2 sine theta. Du is equal to negative 2 cosine theta. That's nice. So negative du is equal to 2 cosine theta d theta. So here's my du right here, my negative du. Okay, and so what do I get? I get 2 times the integral. I could change my limits of integration if I wanted to. The sine of pi over 2 is 1. So 2 minus 2 is 0. The sine of negative pi over 2, which is down here, that's really 3 pi over 2. Okay, is negative 1. So that's 2 plus 2, which is 4. This is going to be 1 over the square root of u, but then I'm going to get a negative du. Okay. So I can pull that negative outside. That becomes negative 2 times the integral from 0 to 4 of u to the negative 1/2. Okay. Du. Now, okay, so now we just add 1, and this becomes negative 2 times 1 over 1/2, which is 2, u to the 1/2 from 0 to 4. Okay. Yes, my
Professor, So usually is the top is gonna be the like in the interval is the top will be the smaller or the
Yeah.
top will be the bigger.
Yeah, you can flip the integral.
Oh,
You can flip
okay.
the integral from A to B to B to A
Oh,
if you
is
just
it
if you negate it.
oh
So
yeah, so
if it bothers you that it's smaller, you can just throw a negative sign in there and flip it around.
okay.
Okay?
Yeah. Thank you, Professor.
It just matters the order of subtraction, but if you change the order of subtraction, you know, if you go 4 minus 3, that's a positive 1. But if you do 3 minus 4, that's a negative 1. So to counteract that, you just throw in a negative, and they're equivalent.
Okay, you got it. Thank you, Professor.
Okay, so this is negative 2 times 2 to the 0 to the 1/2 power minus 2 times 4 to the 1/2 power, which is, this is just going to go to 0. So this is 0 minus 2 times 4 to the 1/2 power. That's the square root of 4. That's 2 times the square root of 4 times negative 2. So this becomes, the square root of 4 is 2. So this is just 2 times 2 times 2, which is 8. This becomes positive 8. Okay, and that's the arc length. Isn't that interesting? That the arc length for your cardioid, right? The arc length for your cardioid, if my computer is done. Let me remove it from the base real quick. See if that helps. Okay. My computer will load here. Okay. Oh, yeah. There we go. Okay, so if we go back to cardioid here, okay, the entire distance around this shape, okay, is 8 units. It's kind of cool. Okay. Okay. Okay, so now let's look at arc length in parametric equations. Okay, so we've done arc length, we've done now arc length in polar coordinates, and now let's do arc length in parametric. Okay, so again, arc length in rectangular coordinates is just a to b of square root of 1 plus y dx squared, okay, dx. In polar coordinates, it was alpha to beta of the square root of r squared plus the r d theta squared, okay, d theta. Okay, for parametric equations, okay, where we have an x of t and a y of t, okay, what the heck? Okay, love it. Okay, let's try that again. Okay, arc and parametric equations. Okay. So again, in rectangular, it was a to b of the square root of 1 plus f prime of x squared dx. We could replace that f prime of x with dy dx if it helps. Okay, maybe it doesn't. I don't know. And polar, so this is rectangular. Polar, L is going to go from alpha to beta. Okay, of the square root of r squared plus the r d theta squared dx, or sorry, d theta. Theta. Okay, and then in parametric, L is going to go from A to B or C to D, whatever you want to call it. Okay, maybe we'll do C to D. Okay. Uh, a circle here, if I parametrize a circle, okay, x equals r cosine t and y equals r sine t. That's the equation of a circle. Okay, and we let t go from 0 to 2 pi. Okay, so again, this is just the equation of a circle with radius r, with center at 0, 0. Okay, it's basically the unit circle, but we're expanding it by r. Okay, so we could let it be any size circle that's centered at 0, 0. Okay, circle at 0, 0 with radius r. And what I want to do is I want to find the arc length of this thing. What would be the arc length of this thing? Well, what's dx dt? Dx dt is r, negative r sine t. And what's dy dt? It's r cosine t. I'm going to plug that into my formula here for my parametric. We're going to go 0 to 2 pi. Okay, and we're going to go the square root of r, negative r sine t squared plus r cosine t squared dt. Okay. Okay, so we're going to parametrize that circle. Okay, circle of r, radius r. Okay, so what are we going to get here? We're going to get r squared sine squared t plus r squared cosine squared t dt, and then I can just factor out the r squared. R squared times sine squared t plus cosine squared t, but again, that's just 1. T, 0 to 2 pi. Okay, and so this becomes 1, that goes to 1. 1 times r squared is r squared. The square root of r squared is r. It's It's really absolute value of R, but that's okay. We can restrict ourselves to positive R's. Okay, it really is the absolute value of R, but let's just let R be greater than or equal to 0. 0 to 2 pi. And then this is dt, right? dt, okay. So this is 0 to 2 pi of R dt. Okay, where R is just a radius. Okay, we're going to treat that as a constant because we're not taking the derivative with respect to R. We're just, that's going to be the radius of my circle. And so this becomes RT evaluated from 0 to 2 pi. Okay. And so if I plug this in, I get 2 pi R minus 2 pi times 0, which is just 2 pi R, which is the arc length. But we have a special name for the arc length of a circle. What's the special name for the arc length of a circle? Remember? What's the special name for the arc length of a circle?
Circumference.
Yeah, very good. Thank you. This is the circumference. A circle with a radius R. That's kind of nice. We were to derive the circumference formula as well, which is kind of cool. Okay, so let's now talk about arc length. I'm sorry, area, sector area. Okay, let's talk about sector area. Okay, we've done our due diligence to arc length. How are we going to get sector area? And what does that even mean? Okay. So, find the area. I don't know what number we're on. We're on number 3. No, we have 2, I think. It should be on number 3. Kind of didn't label my last one here. This is number 2 on the arc length. And so we're going to go on to number 3. Number 3. Okay, sector area. Okay, the area of a piece of a polar graph, sector area. This is for polar graphs. Okay, what's a sector? A sector is just a piece of a graph. Okay, it's a sector. Usually we talk about sectors as a piece of a circle, but it could be a piece of any circular graph, any polar graph. Okay, sector area A is equal to alpha to beta of 1/2 R, which is a function of theta, squared d theta. Okay, so let's look at number 1 here. Find the area enclosed by one loop of the 4-leaf rows R equals cosine 2 theta. R equals cosine 2 theta. Now, if I were to graph this, R equals cosine 2 theta, it would look like this. Okay, it would start out here. Okay, if I let theta be 0, I would get 1. Okay, but then it would go like this. And then it would go like this. And then it would go like this. And then it would come back here. Okay. Kind of spirals around. Okay. And yeah, we get what's called a four-leaf rose. Okay, and we want, what we want is we want to the area of one of these petals. So I have to find out, well, where is it going to be 0? Right? The cosine of what is 0? Cosine of what is 0? Well, that's the cosine of pi over 2 is 0. I know that. The cosine of pi over 2 is 0, and the cosine of 3 pi over 2 is 0. Right? And the cosine of negative pi over 2 is 0. Because these two are the same thing. Okay, but I have a 2 theta here. So what would I want my theta to be? I would want my theta to be pi over 4, not pi over 2, because then I'm going to multiply that by 2 to give me a pi over 2, and then that's going to give me a 0, which is what I want. Okay. And I could also do a negative pi over 4, which will give me negative pi over 2, which will give me, when I take the cosine of 2 theta, that'll get me a 0 and a 0, which is nice. Okay, so going positive pi over 4 units gives me a 0, and going negative pi over 4 units gives me a 0 as well. So that's going to enclose my 4-leaf rose. So I know that theta is going to go from negative pi over 4. Great. Okay. And of course, it got rid of my table, which is great. So much work. 2 theta. Okay. Pi over 4. Pi over 2. 0. Negative pi over 4. Negative pi over 2. 0. Boom. There's my zeros. Okay, so we're going to say that the area is going to go from negative pi over 4 pi over 4 okay, and then this is 1/2 times r of theta. But what was my function for my 4-leaf rose? It was cosine 2 theta, right? Come back to me. Oh, come on. Yeah. Oh my gosh. Stop. Stop bewitching my tablet. Stop. Demons out. Demons out. Okay, so r is equal to 2 r is equal to cosine 2 theta. Okay, so this is 1/2 times cosine 2 theta squared. Okay. Squared d theta. Okay, so let's do the integration on this. So this, I'll take the 1/2 outside. Okay, and this is going to be, let's do a u sub on this. U is equal to 2 theta. Du is equal to 2 d theta. So du over 2 is equal to d theta. Okay, so this is going to be okay, equal to negative pi over 2 to pi over 2, change the limits of integration. This is 1/2 cosine u squared du over 2. Okay. So this becomes 1/4 integral of pi over 2 to negative pi over 2 of cosine squared u du. Okay, so now that I have it in terms of cosine squared here, because I have a positive power of cosine, I have to, or sorry, an even power of cosine, I have to use a double angle formula, or sorry, half angle formula. So this is 1/2 plus 1/2 cosine 2u. I'm going to square that. No, I don't have to square it. What am I doing? Okay, it's just that. Okay, and I'm gonna now integrate that from pi over 2 to negative pi over 2. And this is 1/4 du. So now when I integrate, I get 1/2 u plus, I could do another u substitution here for the 2u, but that's just gonna give me a du, another du over 2. So I'm just gonna say, look, it's 1/4. Okay, integrate cosine to sine, that's sine. Put the u, the 2u back in. Okay, and then that's going to go from negative pi over 2 to pi over 2. We're almost done here. Just got to plug in my limits of integration. If my computer will let me. All bets are off. Come. Okay. Now, what we have is, and this guy is all multiplied by 1/4, right? Okay, so this is going to become 1/8. Distribute that. Well, whatever. Maybe I won't distribute. Oh, who cares? Okay, 1/8 times pi over 2 plus 1/16 times sine of 2 times of sine of pi. Okay. Minus, okay, 1/8 times negative pi over 2. Okay. Okay, negative pi over 2 plus sine of negative pi. Okay, plus 1. So close, so close. Okay. Okay, plus 1/16 times the sine of negative pi. Well, the sine of pi is 0, so that's 0. The sine of negative pi is also 0, so that's 0. So we get pi over 16 plus pi over 16, which is equal to 2 pi over 16, which is equal to pi over 8. That's the answer. Okay. Okay, I'm gonna stop sharing for a second because my computer hates me. I try not to take it personally. But, yeah. Okay, let me do this.